I had the chance to invite Tyler to join us for a technical interview about WheelLab, a sim-to-real robotics project from the University of Washington. His team brought low-cost wheel robots to life from simulation using Isaac Sim and Isaac Lab, two powerful robotic simulation frameworks from NVIDIA's Omniverse platform. I had the opportunity to collaborate with them directly on this project, so you will find tutorials and resources to recreate it yourself on my platform, LycheeAI-hub.com, along with even more robotic simulation tutorials on my channel. Nathan from the Robotics Club YouTube channel is joining me today as a co-host, and together we are tackling many of the questions you have asked in my previous videos, from how to go from simulation to real-world deployment, to performing complex tasks like drifting, using domain randomization effectively, and much more. There's a lot to learn from this interview, so without further ado, let's dive right in. Hi Tyler, thank you so much for joining us today. We are really excited to have you here. Before we dive right into the project that you will present us, can you tell us more a bit about yourself and then about your project?
Yeah, hi, I'm Tyler. I'm currently a PhD student at the University of Washington, and I work on robot learning. And I'm here today to talk about this Wheel Lab project, which is something we did back in January, which is basically enabling sim to real um, on low cost and open source build platforms. Okay, so basically, Wheeled Lab is kind of my vision for this project is to help people do, uh, robotics from scratch. So whether this is like building your own entry level platform and hardware, doing simulation, doing training, and maybe sensors and electronics, and then deploying it to the build robot, and basically the full kind of development cycle is what we're targeting with Build Lab. And this is kind of inspired by my background as kind of a field robotics kind of engineer and researcher. So uh, in my first year of my PhD, I worked on this full scale platform, and I learned all of these skills that I think are really valuable to doing robotics. That kind of they're not as flashy, they're not as they don't get as much attention, but I think they're all kind of very important for doing robotics. And the three tasks from before, so kind of drifting, elevation, traversal, and visual navigation, these are motivated by kind of real world problems. So some of you might be familiar with like the Boston Dynamics Atlas robot. Now it kind of looks different. But for a long time before that, roboticists were really obsessed with this concept of stability. And that's why that kind of humanoid on the left there looks like it kind of just pooped itself. It wants to stay stable all the time. But of course, animals like you and me are very familiar with instability. And in order to drift the vehicle, the robot does have to destabilize itself very briefly, but do it so in like a controlled manner so that it can still navigate through these turns. And then elevation traversal and semantic navigation are things that I'm familiar with, at least working on a full scale platform. So this full scale platform has to reason about bushes, trees, trails, dirt, rocks, things like this, and that's what we call semantic navigation. It also has to reason about the geometry of the terrain, so ditches, hills, banks, turns, things like this, so that the vehicle doesn't completely roll over, crash into a ditch, like as you might see here. Um, these are real world problems, and Real Lab is trying to kind of realize these issues on these low cost platforms so people can still be exposed to them without, of course, having um, $1 million robot and like a full team of engineers to help them with that.
Okay, great. So we are coming to some questions. In the beginning, some introductory questions. So the project highlights a gap between the sim to real, and my question would be, why focus specifically on weird low-cost robots like the Hound for bridging this gap?
Yeah, that's a great question. So I did some kind of review of the current work that exists in robotics. Um, there are just not many great options if you wanted to do kind of reinforcement learning and also do transfer onto a real robot. You have like, at least coming from kind of the academic sphere, most of the platforms that do this are, quadruped robots. So like the Unitree robots or Spot. um, humanoid robots, which are definitely inaccessible to a broader
Yeah.
audience. And then drones are kind of capable of doing something along these lines, but um, of course, they don't. It's not the same space. Like you're mostly just kind of avoiding obstacles, um, and there's a lot of work to be done there. But this is kind of a different side of things.
Hey, cool. So, coming to the next question, what makes Isaac Lab the right foundation for this project, and why not opt for other ecosystems like Gazebo or Color?
Uh, yeah. So kind of in review of these other simulation platforms, um, Isaac Lab kind of developed this. Uh, it kind of developed this kind of a claim for being. Well, there had already been a decent amount of sim-to-real works using Isaac Lab, as it kind of used to be known as Isaac Gym, or was before Isaac Gym. There were some roboticists who were doing kind of hiking through mountains with like a quadruped that was trained in simulation. And so this kind of massive parallelization that happens in Isaac Lab definitely was one of the main contributors for that. And as well as like there's also just like there's all of these sensor simulation capabilities. So um, for instance, if you want to do a task related to navigating complex terrain, you need like kind of spatial understanding of your environment. And so this height scan sensor is also pretty important. That was also in Isaac Lab or Isaac Gym, as it was done before, as well as these cameras that are being simulated. These are all kind of all important aspects of the simulator. And now there's a pretty strong robot learning community as well. So it's pretty easy to work in features that people know uh, kind of works, or even RL algorithms that people have kind of really kind of slimmed down and tuned and all of these things. The community support is also quite strong.
Yeah, I really agree with this one. So, yeah, maybe before we come to the technical questions, who do you envision as the primary users of WieldLab? Like, for example, students in a classroom, researchers that don't have much budget, or perhaps also enterprises?
Yeah, I think it is open to all of these. I think as I was developing it, the target audience was mainly like kind of beginning roboticists. But I have also been reached out to a bunch already from people who are doing research. Uh, as like, for instance, drifting was like a pretty big novelty with respect to the current academic setting. It was like kind of the first work to do drifting without fine tuning in the real world. So there is like uh, kind of a research horizon uh,
Mhm.
on with Wheel Lab, but it is also like it is also using totally accessible kind of infrastructure, and so I do want to kind of see that more beginning roboticists are able to get started with doing reinforcement learning and sim to real.
Awesome. That's great. And as the project is also open source, anyone is invited to collaborate with you, right?
Yeah, definitely. Please, like I think coming from a research background, we don't make the best code. Um, I would say that there's a lot of things that I wish I kind of documented and commented and things like this. But um, yeah, we basically didn't get around to. And I think as people start working on this, they'll realize that I'm probably not an amazing coder. Um, and I think there's a lot of things that could be improved for the sake of the rest of the community and doing things like better and faster and easier.
For the audience, so Wheel Lab is completely open source and they're currently looking for collaborators, even from hobbyists. I've tried a little bit. I think it has a lot of potential. And so, yeah, they're open inviting and they've got great people helping to make the platform better and more accessible for beginners.
So let's dive into some more technical questions. Can you walk us a bit through how WieldLab is interfacing with Isaac Lab and kind of what key abstractions you have made or customized?
Sure. Yeah, I think I have a slide for that. Yeah, so Isaac Lab, I think, in my opinion, already did a pretty good job. I have a lab mate, a friend in the robot learning lab at UW, helped kind of design, and I think he's a great great programmer. Um, he helps like kind of conceptualize this concept of configs, at least for robot learning. And so if you're not familiar already, Isaac Lab has like this manager-based environment where if you look up, like, because it's open source, you can kind of dig into all of the backend code, and you can see that they've written a ton of infrastructure for like calling uh, calling certain components of your configuration structure. So the only thing that you have to do as a designer of these algorithms is just very minimally define kind of certain functions that you want to call or certain parameters that you want to define, like reward weights or friction parameters or stuff like this. And a lot of the backend code has like been written for you that calls all these things. And so we kind of ran with this. Um, at least in this diagram, everything under environment was kind of taken care of by Isaac Lab. These are things that were defined the Isaac Lab by the Isaac Lab programmers, and we kind of extended it into this whole train configuration. So you don't need just an environment to do an RL training. You also need you need to define an agent and its architecture. So like PPO or SAC. And then you also need to define how you're kind of logging things. This is kind of a trivial extension, but it's pretty important for once you start deploying your trained model kind of repeatedly. So in our case, after we got everything training and we want to deploy, say, the drifting policy, for instance, you have some trained model and you just deploy it. And so the faster you can get these or the more you can reduce these iteration times from training to test, it like it greatly improves how much you're able to kind of tune and understand about the problem because you're just doing so many iteration cycles. Obviously, this is not really new. If you come from like an engineering background, you know that this is quite important. So being able to see like your training run and logging it correctly and seeing all the comparisons between all the hyperparameters that you're tuning or changing, and then testing that in the real world and then coming back into the training environment and saying, oh, the vehicle kind of slipped too much. I can change this hyperparameter. Seeing all of this is like quite important for like the whole pipeline. And so that's our main extension. But Isaac Lab already did like a pretty phenomenal job with making for reducing the amount of effort that a programmer has to do.
Yeah, Isaac Lab already covers a lot of frameworks, and that you guys use the manager workflow makes a lot of sense also working in a team. The other approach would be the direct workflow, which I've also covered on the channel before. So yeah, I think that makes total sense. And yeah, coming to the next question, the paper mentioned or highlighted also improving the URDF and articulations, specifically adding like suspensions and refining like steering linkages. Can you maybe talk more about this and how they are like important for the success of the sim to real?
Yeah. Here, let me see if I can get to a good example. So especially for like a task like drifting, which is quite dynamic and quite unstable, the performance of the task is like really sensitive to the actual configuration of the robot and the dynamics of the robot and how it's being simulated. So for instance, yeah, we changed I think the default URDF that we had imported for the musher, which is like the blue car on the left, had the steering linkages going like right through the wheels, which is completely unrealistic and caused some like basically certain steering angles between the real world and simulation were completely different. So those had to be resolved. And also when you drift or when you kind of hit the throttle quite aggressively, it kind of shifts the weight due to the suspension onto the vehicle. Normally this isn't a problem, but for tasks that are quite dynamic, these kind of small changes matter, especially when you're running at 50 times a second and you're trying to perceive changes in your state, trying to adjust accordingly. Yeah, so we basically corrected the steering linkages and added in suspension, which actually happens to be another prismatic joint with like a P gain, which I found was interesting because there's right now nothing in Isaac Lab that actually supports like something called suspension. So we had to add in basically another joint.
Okay, interesting.
But yeah, these things were mainly made to make these like the drifting tasks more accurate.
That might lead me also to the next question about domain randomization, as I believe it plays a crucial role in almost any task, not only for reinforcement learning. And can you maybe elaborate more, like specific parameters that you have randomized?
Yeah. So yeah, domain randomization plays a pretty big role in doing effective transfer of these trained models, at least from simulation to the real world. And that's due to a lot of things, but for one, usually your simulation kind of physics is not realistic. And so, if you train a model in simulation, it rarely transfers directly, and so you'll have to do some tricks. Domain randomization will kind of change up, like you said, like the friction or the mass or something to kind of cover a bigger space. At least this is the theory. Covers like a bigger space of potential real world settings. So in our case, I spent maybe like a week or two trying to just do this through domain randomization of the mass of the robot and its tires friction. Yeah, basically after about a week of just like trial and error from training some kind of setting and sim and then transferring it into the real world and seeing some failures. I actually have like a slide. I don't know if this will play.
Oh, oh man.
Yeah, so there was like kind of this week of development where all of these settings are just completely wrong, at least for the drifting task, and it resulted in certain things. Like we even tried putting a battery on the front of the car to stabilize it. And then I think towards the end of the week, I gave up on trying to find like an effective setting just through trial and error. And so at the end, I took you might remember from like your physics class in high school or something where you would take a spring gauge, just like it's just like this gauge with a spring in it and it has like certain measurements, and if you pull on it a certain amount it tells you how much force you're applying. I basically attached this to the vehicle and just dragged it along the floor, and that basically tells you the coefficient of friction between the car and the ground. And I basically used the setting, so I think it came out to be like 0.4. And then I domain randomized from 0.3 to 0.5 in sim. And I can't say for sure because there's a lot of tricks that we used. I can't say for sure that this is like the one that worked, but it definitely helped. It made the kind of dynamics between simulation and real a little bit closer. So it's easier to debug at least.
I would like to ask something for the visual policy that you guys have trained. So first of all, you simplified the sim to real challenge with grayscale images and also augmentations. I would love to hear kind of why you guys did this, or talk a bit more about this. And also, interestingly, you've shown like a better result with the MLP instead of the CNN architectures. Can you maybe also talk more about that as well?
So if I'm being honest, I didn't have as much of a kind of control over the visual task. my main effort was doing the drifting task and kind of managing most of the project. From what I was told, I think color jittering was one of the main augmentations that kind of enabled the transfer. So this is like changes in illumination and things like this.
Mhm.
And I think Gaussian blur didn't. And I do want to preface that I don't think we ran full kind of ablations and controlled experiments on all of these different factors. Um, but I think what I was told was that like the Gaussian blurring wasn't as quite effective as like jittering. Uh, but again, yeah, we didn't run full control experiments. As for the MLP and the versus like the convolutional net, we do know that this is kind of counterintuitive, and I think the reason for this is more for practical reasons. So kind of the CNN is, or the convolutional net is more of a sparse network. And so we kind of envisioned that it was harder to train. And we saw this as well, like the convolutional net took longer to train to kind of the same amount of reward in simulation. Um, and training itself was also not that kind of simple. You can see the environment there was, you can see that there's like a lot of dead spots. So for instance, like a problem that we had to deal with is, if you spawn the vehicle in on a black tile and there's no surrounding white tile,
Yeah.
it wouldn't learn anything meaningful. It would actually just drive around in a circle and it would kind of collapse training. And so there's all these like kind of additional tricks to ensure that whatever data the robot was collecting in simulation was meaningful data. And I think the convolutional net had a harder time or had a slower time kind of coming up to a decently performing policy that enabled it to actually collect effective data. And so I think the reasoning behind this like kind of result might have been more practical in the sense that like convolutional nets are maybe just harder to train. And given the amount of time that we had, I think the MLP just was kind of easier for the task.
Speaking of training time, I can imagine that the visual policy was the longest one to train. Can you maybe also talk about, in general, what the compute resources were, like GPUs and also time?
Yeah, so the visual task, I think I was told it took around 2 hours for a transferable policy. I think that we ended up using was like we just let it run overnight. So I think that one was a little bit longer, but it usually converges after about 2 hours. The drifting policy, I think, also takes that one's a little bit faster. I think that one takes around 2 hours as well. The elevation policy, I think, is closer. It's in the higher range. I think it's like 3+ maybe hours.
Mhm.
As for compute resources, we all did this on just a workstation, so a computer with a single GPU. I think in our case we used a 3080, and I think that is actually technically under the minimum requirement for the Isaac Lab specification. But if you don't have these compute resources, Isaac Lab also does have like cloud deployments, so you don't need to own the compute that is required for these simulations. You can just run it from some like cloud software.
Yeah, cool.
Would you recommend doing what you guys did, like stacking more 3080s, or using cloud for other who want to follow?
So at least for real lab tasks, I think because our training environments are relatively simple. So we didn't. I guess I might have misspoke. We didn't like stack 3080s. Like we
Oh.
each just individually trained on our own 3080s.
Mhm.
And in fact, we were only like occupying. At least in my case, I was only occupying about like half GPU memory that was available. So I think like it only took like 5 gigs of VRAM.
Mhm.
So it's really not that. At least these tasks are really not that compute heavy. So I think the cloud infrastructure should be totally fine.
Got it.
So I would like to go a bit into specific tasks insights. So you have 3 tasks, like the driving, elevation, and the visual one, and starting with the drifting one. So there you have mentioned that you have a direct sim to real transfer, and I wanted to ask, what was the most crucial element that made this possible?
I don't think I think it's like kind of a quality to doing sim to real transfers that um I don't think there's any one particular thing that makes it like definitely transferred. I think because there's so many contributing factors, that's what makes the problem like really challenging. Like it's getting the steering linkages correct, it's getting the suspension correct, it's getting the friction correct, and then in simulation, it's finding the correct kind of like rewards. You can even push the robot randomly in simulation. That makes it makes the simulation quite kind of adversarial to the robot. Um, uh, I think it's like a kind of a product of all of these things. Um, but maybe in like in all of this progress in drifting, I think pushing around the robot seemed to kind of robustify it. At least from like before pushing the robot and after pushing the robot, I did notice like a bit of kind of more stable behavior. But again, it wasn't the complete picture.
Okay, cool. For the elevation task, this one seemed to be quite difficult as you not only have goal seeking, but also obstacle avoidance and like the traversal. Um, I want to ask, like in general, how did you define the reward function without going too much into detail?
Yeah. So, I think for the elevation policy, the rewards are actually kind of the most difficult part about training them. Um, Mostly because, yeah, sometimes the robots would not want to actually go up a ramp at all to navigate towards the goal. We could have made the simulation environment a little bit more less ambiguous, so like it would have to traverse ramps.
Mhm.
Um, but it was basically a kind of a fine balance between these two things, either just going to the goal or going up ramps. And it was mostly done through trial and error. So if we found some reward setting was making the robot completely collapse to just basically sunbathing on top of these ramps,
Mm.
we go back in and kind of just tune the reward weights and maybe add some um, additional things like continue moving and don't stop it, yeah, stuff like this.
Right. Then for the last task, the visual one, I personally thought it's also a very, very creative way that you guys have found, as it also looks visually very interesting. Can you maybe talk more about the approach that you guys have taken here, and also what the general idea was?
Yeah, uh, just recall that this the high like the kind of the moonshot goal here is to do semantic navigation. So um, there's something that the robot is traversing, and it's either traversable or non-traversable according to kind of your semantic context. In this case, it was much easier to just do black and white. Uh, One, you need some signal from your camera, so it has to be something in color space to make it accessible. Um, and then in our case, like it's pretty easy to just get black and white kind of foam tiles and kind of configure them in a way that uh, is both accessible and kind of easy to change. Um, and at least for simulation, we decided to, you could also just replicate what we do in the real world. Like we could recreate the figure eight in simulation, and I think it would do a lot better. But that's not quite the goal of doing kind of this more general robot learning and then transferring. You kind of want to expose the robot to a diverse range of kind of settings. And so that's kind of what we did in simulation. So those white lines are kind of random walks between certainly like a certain kind of like randomly picked points. And so this random walking creates like these totally random kind of intersections and junctions and whatnot that expose the robot to forks in the road and maybe straights or narrows for a long period of time or turns and stuff like this without us having to actually manually define this environment.
Yeah, I love the idea.
So you were talking about causing the car to have some disturbances in order to drift. And there's something really cool that we discussed earlier is the Scandinavian flick. Can you tell us more about this and kind of the challenges that you resolved?
Yeah, of course. So this is like my favorite part of the project, actually. And I didn't actually get to see this until because the robot is moving so fast and it's controlling its inputs and commanding certain velocities and steerings at 50 hertz. There's just some things like you can't perceive with your eyes. So we have this thing called kind of like emergent behavior in robot learning, where you define some rewards, but through enough simulation and through enough training, the robot learns to do something which you didn't kind of explicitly prescribe. And so in our case for drifting, it was what I now know is called the Scandinavian flick. I didn't know this actually before. Um, but basically the Scandinavian flick is like you can kind of see the robot kind of wiggling around before it takes the turn. And so what it's trying to do is actually destabilize itself. Uh, so Um, so kind of to show you what you're seeing on the right side there. Um, so this is kind of an overlay of a bunch of trajectories. So like there's a bunch of laps that the robot did. We're going to focus on one of them, and it's moving counterclockwise. If you zoom into one of the turns here, you can see that we visualize that the robot has like a certain steering angle and a certain throttle command. So blue indicates kind of cold wheels or no throttle, and pink indicates like hot wheels, which is like high throttle. So you can see as we're coming to this turn, the robot is speeding up, and then as it gets closer to the turn, it cuts its throttle. The wheels go cold, and you can also see that as it goes in, it's kind of like wobbling. So the combination of the wobble and the cold wheels or like cutting the throttle uh, destabilizes the robot and allows it to actually turn and start drifting so that the wheels actually swing outside of the turn. And basically, allows it to turn much faster. So now that the wheels are kind of on the outside, the robot can kind of throttle through this, or basically, as you and I would know it, it's a drift. So as it throttles through this in this kind of new configuration where the robot is facing inwards is providing thrust, it's able to actually turn way more aggressively. And of course, we didn't like enforce any of this. This is all learned behavior just from the rewards that we define, which is like try to slip and then move like really fast, basically.
Amazing what potentials like reinforcement learning has.
Yeah, I think from like a control background, this is behavior that you would otherwise have to kind of mathematically model through kind of really rigorous, whiteboarding and simulation and stuff like this. And yeah, with reinforcement learning, you just give it a couple rewards and you give it some time and it figures out how to do it itself.
Yeah, cool. So I'll maybe dive into the next question. I would like to tackle some challenges and some lessons learned from the project. So especially mentioned in the paper was that the process requires a lot of patience and iterating. Can you maybe elaborate a bit more on like what exactly you mean by that?
Sure, I guess I can talk about this. So iteration is a pretty important aspect of just like engineering in general, but especially in the case of doing kind of these models which are completely black box, um, which basically means that I don't really quite understand what the policy is reasoning about. It's just some neural network that predicts some action to take from some existing state. So you don't get much insight into why the robot is doing certain things, which means that your kind of job as an engineer will shift from kind of understanding what your system is doing, and if it fails, understanding why it failed, to just basically empirical evaluation on repeat.
Yeah.
So you can see here that these are screen captures from weights and biases, which is kind of this web-based uh, like kind of model training and logging infrastructure that we used. So if you're familiar with like TensorBoard, it's kind of a variant of that, except this is web-based. You can see here, like in each column, there's a bunch of these different parameters that I am setting in simulation. They're being logged to weights and biases. And so, I think I kind of, if you mouse over them, they're supposed to tell you which one. So
Mhm.
fortunately, they're cut off here. But, some of these are friction, some of it's mass. And so I'll go in and like kind of tweak these and train a new model. I'll bring that into the real world. I'll come back and I'll take a couple notes and try and retrain a model that doesn't do that. And basically this becomes a process.
So basically, sim to real to sim cycles.
Yeah.
And what would you say on like what was exactly like the most difficult one? Do you think it was like physics fidelity, reward shaping, or perhaps also real world hardware inconsistencies?
What was like the most difficult parameter to close
Yeah.
the gap on? Um,
Probably hard to answer.
yeah, that's a hard question. It is like a lot of components. Like ultimately, the reason is that like the dynamics just don't match between simulation and real, and that can be because like a lot of different parameters. Um, I guess just practically, the thing that caused me the most headache was the friction.
Okay.
um, because I did have this like kind of vision where we would train a policy and it would work across um, like all sorts of different frictions, and I think that's kind of the goal with domain randomization. But we kind of realized in practice that is not really the case, and it is known that if you do domain randomize your kind of simulation, you just get a really conservative policy that works or tries to work in all of these domains, but really it's just the worst of all of them. Um, and so you have to be a little bit more specific. So domain randomization can't be like the final the complete picture.
Yeah, makes sense. Were there any aha moments during the development that like made you change dramatically or improve dramatically the sim to real transfer?
Uh, I think some of the reward terms helps, and also getting the spring gauge.
Hmm.
Yeah, I think well, I spent like in that week that I was trying to tune the friction parameters. I was occasionally kind of looking for a spring gauge, and I was kind of running around the robotics lab asking people if they've seen a spring gauge. Um, and I didn't find it until the very last day of that week, and so that's when I like I got the spring gauge and I ran back over to the room and um, yeah, that was exciting. So I guess I don't know if that was an aha moment. Um, and then I think one of the reward terms was kind of it was uh, enforcing that the robot keep up its speed through turns,
Mhm.
and I think that might have also helped. At least like uh, I think I noticed some behavior where it was hard to actually before that reward, it was hard to get the robot to actually kind of throttle through the turn, kind of like keep its wheels hot through the turn. And I think adding the reward in that uh, told it to keep up its speed through a turn helped get this kind of hot, I guess, turning.
Mhm. Cool. Yeah, that was very insightful. And you might want to tackle some real-world performance questions. In the paper, you have kind of mentioned that you're inviting the audience to challenge the robot. And my question there is, how well does the different policies handle the external disturbances and like variations in the real world that are not explicitly trained?
Yeah, so the drifting policy right now is quite sensitive. This is something I'd really like to improve upon. I do note in the paper that like adaptation is something that I'd really like to kind of work on. I imagine if you try and perturb the robot as it's drifting, it will probably spin out. It'll know how to recover, which is really interesting. That hasn't really been seen before in literature. But this one is quite sensitive to perturbations. Um, the elevation task, we actually uh, funny story, because like we're getting the global elevation kind of from our motion capture system. You can do it without it, by the way, but in our case, when we were evaluating on these like really high frequency features, it was easier just to use a motion capture system.
Mhm.
And one of our, um, the motion capture system works off infrared cameras, and one of our lab mates' shoes were reflective of
Wow.
of this infrared camera, and so um, if you labeled the shoes as an obstacle, we actually got the robot to avoid our lab mate as he was walking around the scene. Um, so
In real
because
time?
yeah, because everything is on board. So the like if we move these, like we don't do it here, but if you move these obstacles around, it will still continue to reason about them. It's running at like I think it's running at this is also running at 50 hertz, I think, or 30 hertz or something.
Mhm.
So we don't test it here, but this is totally possible. And I think same thing with the visual task. I lay down these tiles here, but we can also lay down white tiles or something like this.
I love the adaptability of these. Like it's very robust
Yeah,
data
yeah,
set.
and this is like the benefit of doing kind of real time uh, control. They are reasoning about the system at like certain control frequencies, which enable it to do these more dynamic kind of behaviors.
Now, I also like to talk about more about the future work and the vision. But first, maybe I would ask, which limitations did you have when working on this project?
Yeah, so I think um, because the eventual goal or kind of my goal for the project was to kind of bring on more people who are maybe unfamiliar with this full process or want to get started with reinforcement learning. Um, you still at least these train policies right now have to be kind of patience, especially the drifting one. Um, But that's not to say that, it has to stop there. I think like I was mentioning before, if it in theory it's totally possible to train a policy that is kind of adapts to different friction parameters. So I think that would be really cool if we just like upload some a model that is capable of adapting to friction and on your side you just download the model weights and you upload that to your robot and it just starts drifting. I think that'd be really cool.
Mhm.
Um, yeah, and then I think, also might be kind of a function of the limited compute and sensing that these platforms can provide at low cost. But, like I said before, we do have a motion capture system providing these high frequency features. And that's because I think, depth cameras right now, or at least like the elevation mapping procedures that are available that are open source to these kind of low cost robots. Uh, when we tried testing them in this config like in this setting, they were really noisy. It's possible, like with good training or a good simulation environment, it could reason about the noise and still navigate through the environment. But um, that's another limitation. That right now you at least have to, if you want to do this elevation task, you'll have to define, at least on these, like if you have really sharp features like we do, you'll have to define these beforehand. Um, and then The visual task is also limited to right now just black and white, but and this just makes the transfer easier. So depending on what your goals are for trying to learn about kind of doing camera transfer, you could make this problem harder in simulation and try and bring that into the real world. Grayscale just happens to be kind of an easier domain to make the transfer possible. Yeah, so right now I'm trying to write up some kind of tutorials around the project, and I'm looping in some of my collaborators as well. The ones who worked on the visual task. He was actually the one who did the perception model for the full scale robot. So he's kind of amazing at perception. Um, yeah, so tutorials for around Real Lab, and I think as we start to get more feedback from maybe like the viewers or everyone who wants to work on Real Lab or even just want to try and get their car to drift, um, I'm really interested in seeing what the actual problems are for other people in either like non-academic settings or hobbyist settings or things like this. How hard it is to actually get these things to work, and if they are hard, what can we do to make them easier? Or what are some things that you know you guys have changed that we could kind of work into Wheel Lab? And is there like a bigger research direction there that just in general tries to make low cost robotics a little bit more accessible, at least for robot learning, from a robot learning perspective to more people?
Now that you have also mentioned the community, for those viewers out there that are inspired by this project, how can they get involved, contribute, or like try Wheel Lab themselves?
Yeah, I think a great way, at least right now, I'm also open to, or like I'm new to the kind of um, the open source domain, but from my understanding, you can kind of raise these issues on here, where it becomes known to everyone who is like viewing the repository that there's like certain issues right now that we're aware of that we're trying to fix. Some people, like we've already had some contributors um, make some changes to the code, and then we can merge that in. I'm new to this, but apparently, like there's certain rules and like kind of contribution expectations. I think for now, this is like just going through the GitHub is a good way to get started. And also, anyone is welcome to kind of shoot me an email or just DM me about um, problems that they're having or how to get started, just on an individual basis as well.
Yeah, awesome. And we are also working together with you. So everything and all the tutorials will also be hosted on the platform on LycheeAI-hub.com, where we are working also together on helping and also looking for people to collaborate. And like you've mentioned, I think GitHub is probably the best way to directly contribute to the project. And I would maybe have one last question: is what's the one piece of advice you would give someone that wants to start their own sim2real project with low cost hardware?
I think as robot learning uh, invites kind of, it's becoming, at least, we're trying to make it more accessible, but I have noticed that there's, at least in the academic sphere, there's like more and more kind of different areas coming into robot learning and trying to kind of make it work. For instance, from language or from large models and other areas. I think it's always good to remember that robotics is just inherently interdisciplinary. So it's good to keep like kind of an open mind about different areas that you may not have a lot of background in, because robotics is so interdisciplinary. The solution to one of your problems of many might come from a different field. But to me, that's like the most exciting part about robotics, that you're never focused on any one particular problem, but and even if you are, it's usually introduces you to kind of a field or area that you weren't originally familiar with. So, for instance, for drifting, you do have to become somewhat familiar with kind of network architectures and different training algorithms and stuff like this. And I think that's really exciting. So basically, in short, maybe just keep an open mind about where your potential solutions can come from. It could be from different areas.
Love that. It's great advice.
Yeah, and thank you so much in general for all the insightful information that you gave us. I'm pretty sure anyone that is watching will learn at least one thing, and I'm pretty sure most will learn a lot of things about sim-to-real robotics and Isaac Lab. And definitely we have learned a lot when talking to you the first time. So I'm hoping other people also find this very insightful.
Yeah.
Yeah.
Yeah, I hope so. And I'd love to I think I hope that I'm a good teacher. So I would like to kind of see, if people do have questions, I'd love to answer them. Um, I think teaching is a good way for me to challenge my kind of assumptions about certain things. So please do ask either on GitHub um, or I don't know if you have kind of like a communication network, maybe like through Discord or something that uh, I'd like to try like actively engage with.
Everyone is welcome to comment on the video below. And I think you can give your feedback there and also tell us what you're working on. Again, thank you so much for coming and sharing all your information and your knowledge.
Of course, yeah. Thanks for having me.
I hope you were able to learn a lot from this interview. You'll find all the resources linked in the description below, including the platform where we walk through tutorials for Weird Lab, so you can try it out yourself. If you enjoyed this video and want to see more content like this, make sure to subscribe and give it a like. It really helps the channel grow. And if you'd like to support what I'm doing, you can join me on Patreon. There, you will also get access to my Discord community and exclusive content around Isaac Sim and Isaac Lab. Also, right after this interview, Nathan had a one-on-one conversation with Tyler and uploaded it to his channel. Be sure to check it out to hear more about Tyler's life as a PhD student. Thanks for watching and see you in the next one.